Our third speaker today is Mr. Alexander Alzamora. Has a presentation titled Practical Case Study on Cement Industry Waste Heat. Mr. Alexander, I think he is based in UAE right now. He has an MSc in Mechanical Engineering from University of Patras in Greece. He is technical qualifications in complex thermodynamic systems. He's also senior manager of industrial applications for NG Solutions, the company. Alexander is responsible for the effort to decarbonize heavy industry by facilitating the adoption of energy efficiency measures aimed to reduce specific energy consumption of energy-intensive processes, such as the case study that he will show us today in the cement manufacturing, also in metallurgy and other food production industries. He has lots of work in UAE and Saudi Arabia and Bahrain. So the floor is yours, Mr. Alexander, to present your work.
Thank you very much, Dr. Majid. I will share my screen, and please let me know if I am audible and if my screen is visible. Can everybody hear me?
Yeah, we can hear you.
Very well. So, yeah, my presentation is a practical case study in the cement industry and the application of waste heat recovery technologies in water-scarce conditions. The outline is, I will start by making the case of waste heat recovery in the cement industry, then moving on to present the available technologies for waste heat recovery in the industry, and then a rationale, what is our rationale for choosing one technology over the other, and then doing a brief presentation of the technology of the ORC, or organic Rankine cycle, how it integrates into the cement process, what is the process flow, a technical comparison between both technologies, and then looking at some safety concerns. And finally, we'll be looking at the financial considerations of both technologies and what are the available financial models for companies to integrate this technology. So the case for waste heat recovery in the cement industry, basically we have the fact that market dynamics dictate the need for constant process efficiencies improvement as demand pressures drive cost optimization. So basically we have events such as the 2007 financial crisis, as COVID. We have a cyclical economy, and at every, let's say, low bottom of the cycle, we have pressure on industries that basically drive the demand for cement. When these cycles occur, the cement actors, the industry players that have the best efficiency on their production costs are the ones that survive, are the ones that can make it through these cycles without heavy financial burdening and so forth. So there is a clear a drive from the industry to continuously improve their process and continuously improve their cost. Then the fact that the cement industry is extremely dependent on electrical power to run its process. The cement industry is a high thermal process industry. However, the electrical consumption is extremely substantial, as there are several elements such as the mills that require very large motors, and that requires a large amount of electrical supply. Then, as I was saying, the process is thermal in nature, and therefore the clinker production process generates very high amounts of waste heat. You can quantify them at around 5 to 6 megawatts of thermal energy per 1,000 ton per day of production capacity. So a plant of, say, 10,000 tons per day would be generating about 50 to 60 megawatt of waste heat, which is a significant value, and obviously it would be very, very beneficial to be able to utilize. Then the fact that waste heat from the cement process can be recovered with no impact to the production process. So again, there is obviously there are several process optimization and energy efficiency measures that have to do with the core process in every industry. This applies to all industries, but these energy efficiency measures oftentimes are not really attractive to the plant operators because of the fact that they will end up impacting the process, and there is a little bit of uncertainty on whether that impact is going to actually affect beneficially or not the plant. So you end up in a situation where plants are actually trying to increase energy efficiency, but end up doing quite the opposite. Waste heat waste heat recovery is definitely something that requires some study to implement into the process, and we'll see a little bit more detail later. But it's a relatively non-intrusive technology. And then the fact that power production from waste heat is one of the major energy efficiency improvements that a cement plant can actually do, other than using alternative fuels or refuse-derived fuels to decrease basically their fossil fuel consumption. Waste heat recovery is indeed the largest contributor to carbon footprint reduction in the cement industry. So all these factors contribute to us saying that, asserting that yes, waste heat recovery has a very special and significant place in the cement industry. Now, what are the available technologies for the cement industry? So first, the optimal use for the utilization of waste heat in any industry is to match it to what is called heat sinks in the process. In the cement process specifically, the heat sinks are the raw material and the fuel drying requirements. So this is where we will utilize primordially the waste heat that is being generated by the plant. However, these account for about 20% of the total waste heat that is being produced by the plant, and therefore they are unable to absorb the totality of the process waste heat. So we therefore conclude that the optimal use of waste heat in the cement industry is to use that heat to generate power. As we were discussing before, electrical power is a major cost driver for the cement industry. So we can utilize the waste heat to generate power and decrease the electricity consumption of the plant. The available technologies for this are basically two. One is the old and well-known steam Rankine cycle. It's a quite water-intensive process, which is recommended for seasonal climates where you have seasonability of large swings between the temperatures, the ambient temperatures, and also, and this is one of the main things, that it requires water abundance. And I will go into further detail on the water requirements for the steam Rankine cycle later on. And then we have the organic Rankine cycle, which has the potential to be a completely waterless system. There's absolutely no requirement for the water for running the process of the organic Rankine cycle. You can, if you want, you can use water cooling towers, but it can function very, very well without the use of any water in the process. So just because of this fact, we see it as the preferred technology for climates where water is scarce, which is actually the case for the GCC and Bahrain. The performance and the efficiency of the system is very, very much dependent on the environmental conditions and the availability of water. So the rationale for choosing organic Rankine cycle in arid climates is that the water is extremely scarce and very, very expensive. And therefore, any sort of water-cooled system will end up having a very high operational cost. The other fact is that ambient conditions with high temperatures are not as conducive for air-cooled steam condenser systems due to basically high dry bulb temperatures that limit the temperature that the steam can actually condense, and that in turn affects the performance or the potential efficiency of the steam cycle. And lastly is that the organic fluid thermodynamic cycle exhibits a much lower enthalpy drop than steam, and we will see a little bit more detail further down the line. So now we have established the rationale for our choice of organic Rankine cycle as the technology of preference for arid climates. Let's see how it integrates into the cement process. So in the cement process, we can recover heat from two sources. The main, let's say, producers of waste heat are two sources in the process. One is the preheater gas, which is where the combustion air basically goes, and you can, it's this part of the plant. This is the cement plant. This part is the preheater, and here's the combustion from the kiln, and the combustion gases are preheating the raw material as it drops, and then basically going out to the stack. So this is one of the sources of waste heat that we can utilize. And then the clinker cooler gas, which is after the cement has been produced, the clinker has been produced within the rotary kiln, and it has gone to what is called the clinker cooler, which is basically an air-cooled system that pushes fresh air into contact with hot clinker and cools it down. And the effect is that there is hot air coming out that needs to be ejected through the stack. So these are the two main sources for waste heat recovery. And here is where we integrate basically the process by integrating heat recovery boilers or heat exchangers into these two sources. And we will see a little bit more in detail the actual schematic of how that is done later on. But we need to have some process dynamics in mind. I was discussing about how it's not intrusive, and it is really not. We can actually have a system in full bypass. However, when integrating, we do need to be mindful of the pressure, and the working pressure in the system. We don't want to alter the pressure equilibrium within the process. Also, we need to be mindful of what is the filtration system. There are very substantial differences between standard and traditional baghouse filters and, for example, electrostatic precipitator type of filters. And then obviously we need to be mindful of not taking all of the waste heat, but giving always the priority to the requirements of the dryers of the raw material and the fuel. So a little bit more of a technical schematic, as I was discussing. Here is in a more schematic representation the cement process. This is the rotary kiln. This is the clinker cooler, and these are the preheaters. So I was saying waste heat exits the preheater and normally goes into the raw mills or whatever thermal requirement, and then goes to the stack. Here we would do an intervention, and by adding one damper here, we would be intervening and basically taking the waste heat into this waste heat recovery boiler, and this would be heating up thermal oil as the heat carrier for the process. And then the hot
Alex, you have 5 minutes to go.
Sure. And then the hot oil drives the organic fluid in the turbine, and the whole cycle basically restarts again. As I was saying, the system can be bypassed, so there is absolutely no issue, and it can be completely independent. And if there's any issue, the plant can continue working as normal. Some differences between the steam Rankine cycle and the organic Rankine cycle is, as I was saying, this organic Rankine cycle has much smaller enthalpy drop. It doesn't need supercritical pressures in the cycle. It doesn't need to be superheated, and there is no risk of blade erosions, in contrast with a steam cycle where due to condensate within the turbines, there might be a chance of mechanical stress. The main point is that there is no water treatment, and it's a water-free system. It requires minimum personnel as opposed to the steam cycle that needs a highly skilled operating team. No major overhauls because of no erosions, and it's a completely automatic system. And also, one major point is that it has a very high flexibility when working at part load condition, so it can operate at 90% of its nominal efficiency when running at 50% partial load, as opposed to steam, which can run at 70%, and it can run at 80% of its nominal efficiency when the system is 30% partially loaded, whereas with steam we have efficiencies of about 55%. Some safety concerns regarding the ORC, organic Rankine cycle, due to the presence of thermal oil. It's absolutely safe. There's concerns always of fire within the thermal oil system, but it's absolutely safe. There's no risk of explosions, whereas in contrast, the steam cycle needs to work at a very high pressure and therefore presents a higher safety risk due to the pressure concerns and the operational pressures. And therefore, due to the nature of the thermal fluid, even though it's operating at a high temperature, it is absolutely safe due to the fact that there is no vapor concentration. Even if there's a leak, the heat will the vapors will not concentrate; they will actually burn and generate smoke. And the thermal oil in general cools quite rapidly when exposed to air. Just going towards the end, some financial considerations. The ORC versus the SRC. As you can see here, for the same amount of load, we have a little bit higher efficiency on the steam Rankine cycle, whereas the auxiliary load is much higher due to the requirement of having air-cooled condensers. This results in, if you see also the capital investment of the ORC is relatively higher, is a bit higher than the steam Rankine cycle. However, due to the fact that the operational costs are much higher on the steam Rankine cycle, we get to a levelized cost of electricity, a lower levelized cost of electricity for organic Rankine cycle than steam Rankine cycle. And that within a period of 20 years means very, very substantial savings using organic Rankine cycle. I'll just very quickly discuss about the models available for financing these plants. So one is the CapEx model, where the plant carries all the implementation risk. The plant carries the operation and maintenance risk, which requires a complete diverse team from the normal operation. Plants don't like that. Plant carries the performance risk after the end of the performance guarantees. And in general, the EPCs offer liquidated damages that are limited to the achievement of commercial operation dates, and also availability liquidated damages, which are subject to adequate operational maintenance. Whereas there is another, the second model is the build, operate, transfer, which is a finance solution in which you have a developer that carries the implementation risk, a developer that carries the operational maintenance risk, and the performance risks through the term of the contract. Okay, and this is just finalizing. We recommend for plants to go actually with a finance solution model because they won't carry all the risks. And then when looking at the only thing that has to be looked in detail is when looking at the finance model, due to the developer needing to account for this, the cycles and the market risk of the business. They offer oftentimes two options. One is a take or pay with a fixed rate contracts, which is not really preferred by cement plants because then they have to account for the fluctuation in their business cycles, and this doesn't really work for them. It doesn't do that for them. And then the second option is the flexible rate and term, which is an innovative approach to these type of contracts with main features, modulating rate to accommodate the plant utilization fluctuations, and an NPV basis for the determination of term. Basically, the term will elongate or shorten according to the performance of the plant and the achieving of an NPV within the contract. Finalizing, just a visual of how ORC system looks like integrated into a cement plant. And that's it. Thank you very much for your time. And if you have any questions, you can contact me in the below email.
Thank you, Alex, for this presentation in which you have applied thermodynamics from mechanical engineering point of view into an industry which is located in arid environment.